um, some operational behaviors, right? So once we get to know about how the things or how the microgrids operate, then we can definitely dive deep, right? So here are some control variables. So what are the control variables? Voltage, active power, frequency, and reactive power. Okay. So mainly the microgrids, we have some of these parameters. We need to take care of this voltage because of the synchronizing behavior that we need to maintain. Okay, the active reactive power and frequency, these are the basic characteristics that we need to take care of, right? So because for the frequency or voltage, these are the basic characteristics that we need to maintain uh, right upon the system behaviors. Okay, so and also the active and reactive powers. The active and reactive powers, reactive powers. These are mostly characterized upon how the power sharing can be continued or can be uh, power sharing can be driven at large. So how the power sharing would be taking place in the microgrid, that should be our major aim in maintaining or in monitoring these active and reactive powers. Okay, so mainly there are some connective modes or behaviors like grid connected mode or islanded mode of operation. Okay, grid connected or islanded mode of operation, and in between these grid connected and islanded mode of operation, there has to be a proper balance. Okay, and the frequency of these behaviors that are characteristics that has been detailed here should be maintained at large. Therefore, our primary aim is to have a uninterrupted power supply, and also in some cases they should also have the capability to uh, deliver black start. Okay, okay, let me see here. Okay, I think it's Yeah. Okay. So thereafter, uh, also the aim is to optimize the operational cost, because after all we need to maintain the system cost within the predefined limit, and for that thing these control variables play a major or significant role. Okay, and since the microgrid framework is quantitatively a new framework, that's why the major aim of this microgrid architecture is to uh, deliver uninterrupted power supply as in the case for uh, the grid connected mode of operation. So in grid connected or by the to be delivered by the grid. So our major aim needs to be fulfilled. So for that purpose, here we have also the hierarchical control where this is microgrid MG area 1. Okay, microgrid 1, and similarly this entire thing holds true for MG2, MG3 up to MGN. And this is the, let's consider the case where the substation is there, and after that the breaker is there, and after this the entire distribution grid is subdivided in this microgrid 1. An entire grid is subdivided into 2 or 3 microgrids. Entire grid is after the 33 by 11 kV node. So the main problem or main issue or main challenge lies is that there in individually we need to monitor all the microgrid 1, microgrid 2 and microgrid up to microgrid n. So when we need to monitor them all, the basic fundamental, when we need to monitor them all, the fundamental criteria or behavior that we need to follow up is to maintain the central or emergency control. We'll have to also maintain the secondary control and the local control itself, right? So the for the major problem lies is that when we have to control them individually, and after that we need to deliver that information to the uh, central operating substation, that is where the DSO is located, distribution system operator or DNO, distribution network operator. They monitor each of these subsection or sub areas carefully, but there is a problem. What is the problem? The problem lies with uh, accurate installation of the metering devices, and since each and every area has to be properly monitored, because in the smart grid architecture the smart grid uh, is only due to the uh, cause of what we say that uh, the smart grid the smart grid is considered a smart grid because of the monitoring and control actions, control behaviors with various features that we have discussed previously, like demand response schemes. But here, our major aim is to provide accurate control, and once we have the ability to control them properly, then only we can actively say that this part of the system is being dedicated for this portion of the system is delivering accurately or not. But before that we need to have proper monitoring and control action. So one central controller is there at the DSO, and individually individually they interact with the individual controllers that is placed in each of these microgrids. Okay, so this can also be termed as MVLV nodes. Let's consider one HVLV node. HVMV node, and below one HVMV node there are multiple MVLV nodes. Okay, and for individually these MVLV nodes will have to place proper metering devices, and these control actions that will be informed by the uh, head, or you can say rather the central controllers. They will have to deliver the information. They will have to have the information from all these MPLV nodes. Okay, so from the general block diagram scheme that we can see, the distribution system operators need to manage each and every microgrid separately, means centrally as well as separately. Okay, so the other problem lies here is that we'll have to also play a part in electricity market, and nowadays electricity market electricity markets are uh, being overlooked in many cases, but these electricity markets do play a subsequent role in around 5 to 7% of the entire electricity demand that we get nowadays is being delivered by the electricity markets, and they just not only have the ability to we can say rather to earn more profit in the system by, because the aim of this electricity market will have to earn profit. Okay, so to earn more profit, that's why the private entities are getting more and more engaged with this electricity market actions, and thereafter they are delivering a global, I mean, sorry, not global, we can say the, from the Indian context, you can say in our country's purview, they are trying to deliver at most 5 to 7% of the total demand, but in context of market. But again, on the other hand, we can't just increase the price to earn profit. We'll have to also look after the social needs or the local needs, and in these local needs we'll have to maintain the power quality, the efficiency. Okay, so we'll have to make a balance between this profit and the power quality, balance between the efficiency, and after that only these entire microgrid architecture that we had been discussing, they can play a proper role in the current or modern day uh, platforms in the market analysis or everything. So there are also the part of local controls. These local needs that we have discussed, the local controls can be characterized by, you can say, local controls. We can say that uh, some control hardware actions. Okay, then we can also say some voltages of the DGs voltage. Okay, so these things will have to take care. Okay, and we'll also, in the meantime, we'll have to maintain the stability of the system. So again, with the since we have all these things in hand, we can also take care of some other control features. Okay, like these these local controllers, these local controllers they have the capability with two mode of operations. Okay, so we'll have the voltage source controllers, and here the voltage source controllers, and here the reference voltage. We'll have the reference voltage which is provided by the group controllers. So we'll discuss next what are the group controllers. So here some PI, this we also know this the proportional integral controllers, PI controllers are used. The proportional integral controllers are used, and they are widely used to have some control actions from the local local objective. Okay, so here are some of the one example of the group control where both the we already know that P and uh, is the real power. Real power is mostly drives the frequency of operation, and the reactive power is mostly driven by the mostly drive the or maintains the voltage. Okay, so here's an example where we can see that the group control here DG1 and DG2 two characteristics of two DGs are shown here, DG1 and DG2. Here, for a change in Q from this to this one, there's a voltage drop from this to this one. But here, for a longer amount of change from Q2 to Q to 0, means this del Q1 and del Q2 are different. But for both of them, the change in V is same. That is del V remains same. So that means uh, these are the characteristics of the local or hierarchical control where both of the devices or both of the DGs, these are uh, dependent upon the DG characteristics. So uh, it varies, and that we need to take care of because like the generator we have the ramping limit, there are some constraints. These are also kind of we can say that there are constraints or limitations because we cannot directly uh, choose between a proper control measure we cannot directly take into action. Okay. We'll have to choose properly which device is delivering which result, and accordingly how fast the control actions can be obtained, means after the control actions being taken how fast the system would respond to the change that or the action change that is being prescribed by the what I would say from the device or from the we can say the devices or the installed equipments. Okay, so 5%, one example was also given, that 5% group. What do we mean by 5% group? That there are 5% change, 5% deviation or change in frequency would result in 100% change in power. So that is meant by 5% group. Okay. And these are also cases for the generators. Okay, means the 5% group, these group characteristics are also uh, available for the generators, means the synchronous generators where based on these group controller group characteristics we can say about how the dispatch would be delivered and what amount of dispatch would be delivered. Means suppose we have a demand of 500 megawatt, and how this 500 megawatt would be distributed amongst two or three or five generators, and based on these group features and how fast they can respond or they can maintain the when the AGC loop starts operating, how fast they can maintain that 5%, but they can maintain that operational behavior with a 5% change, or rather we can say the x amount of change in the loop. Okay. So these individual DGs here, since we are all talking about DGs, because here we are mostly concerned with microgrids. So since these DGs, multiple DGs, they track these changes to take care of the to accommodate and say this change. Okay, so from the P and frequency characteristics, we can say that F minus F naught is proportional control P minus P naught. So, and Kp is, which is in hertz per unit, which can be represented by del F by del P. Okay. So change in frequency here and change in power. So how are they characterized, that we can understand. And similarly, that is also the case for Q, which also says that V minus V naught is equal to minus KQ Q minus Q naught. So here KQ is also given by, that was volt per PU, and this is volt, that was hertz per PU, and this is volt per PU, and that is gives del V by del Q. So these are the group characteristics and behaviors. Okay. So, but there are some drawbacks also for the group characteristics or group behaviors. But so we can here itself. Okay. So some drawbacks we can discuss. So one of the major drawback is that when we uh, have, means a small mismatch, means when we have a small mismatch, that can definitely impact the sharing of the equipment, sharing of this power. Means if there is a small mismatch in small mismatch, and what mismatch? That is the grid impedance. Then only we can grid impedance. Then we will have a improper sharing. Okay, and also it is unsuitable for nonlinear characteristics of this behavior. If the characteristics are nonlinear, so then that will also cause a problem or harmonic distortion. Also, if there are poor voltage regulation. So these are probably the three main drawback or reasons. So so once we have the poor voltage regulation, that will definitely impact the reactive uh, power. So to cope up with them, we have some improved group control behaviors or characteristics or features, we can say. So one of them is some adaptive techniques, adaptive group control. We can also have the angle group control. We have virtual impedance. Virtual impedance method. Then we have uh, virtual frame transformation. Okay. And lastly, we have virtual inertia based group control. So first we had the drawbacks, and after that we had some of the group control activities which can facilitate in delivering better results. Okay, so these are the primary controls, and based on some primary controls we also have some predictive control actions. We also have global control, we also have the central control. So in adaptive group control, generally we what we mostly do is that we will have to try to improve the voltage regulation. Voltage regulation improvement. Also, in the angle group control, we try to improve the low frequency deviations. Again, in the virtual frame of transformation, we try to use the orthogonal transformation matrix to improve their feature. Okay, in the virtual frame of reference. So, and therefore the reactive and reactive power uh, changes of active and reactive power flow equations to get transformed to a new reference frame. Okay, then we have the virtual inertia based group control, where we can definitely improve the uh, try to improve the inertia so that some control actions would be initiated in the absence of inertia. So we try to deliver inertia in the system, therefore to prevent some mal-operation, we can say that. Okay. So these are the primary controls. Some we also have the secondary control. These are the primary control. Now we have some secondary control actions where the main aim of the secondary control is to provide the communication based method for parallel operation. Okay, so okay, so let me write some. So it allows power sharing. Okay, so it allows power sharing with uh, parallel configuration of DGs. Okay. Also, we have the central controller. This is operates on a slower time scale because firstly the primary control will have to respond, and after that the secondary control actions would initiate. So that's why these actions would be a bit slower than the primary control because they will have to have certain amount of time before they should be operated. Okay. Now the central or emergency control, where the that is the DSOs or DNOs, we can say they can finally they can finally uh, take part in the microgrid supervision activities, and these are centrally operated. We can also say that microgrid uh, energy management system. Okay, so they are also capable of islanding, performing islanding on grid connected mode or behaviors. So these are mostly controlled by the central upper control, hierarchical control. So these are mainly the uh, predictive approaches where some model predictive method, consensus based method, they takes a major role in delivering the proper actions, and globally we'll have to have some controlling features that are present in the central control facilities, and they are restricted in the what we can say the primary, or we can say the secondary control. And will this global control thus, or therefore this global control will lead to a proper or finally these are the final controlling behavior that we get from the entire operating or the entire microgrid in operation, because they works in network mode as well as they works in islanded mode. Okay, so some intelligent control techniques are also being deployed nowadays with we can say uh, these are meta heuristic approaches for some meta heuristic approaches like genetic algorithms, you can say the fuzzy approaches, fuzzy logics or fuzzy approach, and the approach based controllers. Also, you can say some PSO based controllers. We can also say some ANN based artificial neural network based controlling actions. So These are some of the intelligent control techniques that are globally centered at uh, the powerhouse of this entire microgrid or network microgrid, we can say, or connected, interconnected microgrids or islanded mode of operation, because they are responsible to deliver the proper control actions. Also, we have neurofuzzy controllers, etc. Some adaptive schemes. Okay, so generally the these microgrid control architecture. So first of all, the appropriateness of the control action should be deployed. Okay, and this hierarchical framework that we have discussed. So this lays the in better we can say load sharing activities, because after all we have some interdependencies, like suppose we have more loadability, more loads in area 1, and we have less loading scenario in area 2. So in that cases we will have to, means since they are connected, so there can be load changes or load sharing are being done between these two areas. So those cases also can be properly handled. We have this hierarchical frame of operation of the microgrids. Okay, so some decentralized control activities can also be employed, because overall the information that is being delivered by, or information that is being delivered to the control station, for that this decentralized scheme will also uh, deliver a better response to the entire system. Okay, so with the with this we are done with this distributed control, decentralized control. Okay, now we can discuss a bit of how this DC microgrid control. This was the AC microgrid control, right? So now we can have some discussion on the DC microgrid control, or decentralized control of the DC microgrid, distributed control, centralized control. So primary aim of going towards or moving towards the DC microgrid architecture, DC microgrid, is to have, because we have some loads, we have various loads which directly operates in DC. Mainly the light loads, that is the incandescent lights. They work in DC. Also, we also have they are resistive loads. So for that purposes, mostly when the lighting in the evening part, when we have major light loadings, in those cases, if we can directly transform the means we don't need to transform the, because the solar is generating in DC, and we if we can store them in the battery itself, that is also in DC. And when both of them are working in DC, and mostly we have the solar battery, wind, although wind is in AC, so we'll have to permanently convert them to DC. But when most of these cases, ultra capacitors and all these things, when they are delivering directly in DC, so what we can do is that we can directly utilize the energy which is stored in DC, and accordingly we can utilize them. So the converter banks, the converter stages are reduced significantly. And with this, the harmonic injection is also reduced, because the harmonic reduction, with the harmonic reduction, the amount of losses gets reduced. Because when we have the fundamental component, let's consider I1. So I1 is the fundamental component, which is uh, let's say I total. So I total, if there is only fundamental component present, then it's same as I1. But if there are the harmonics present up to third order, fifth order harmonics, seventh order, ninth order harmonics are present, then the total value that comes here is I naught, means I naught plus square plus I naught square 2 and dot, and after that we need to take the square root. So I need to check once whether this should be inside or outside, but overall that is the entire thing. That so here I total with harmonics, this value is not same as I total. Okay, I total harmonics is definitely greater than I total. So that's why our main aim is to reduce the converter stages, which can significantly reduce the harmonics. And once the harmonics are also reduced, so losses are also reduced. So first of all, we have the three types of control behaviors or controls actions that we have in the DC microgrid control. Here first is the decentralized control. So in the decentralized control, what we can say is that each of these sources, means each of these areas operate as independent using terminal informations. Okay, and also reliability is also maintained. Again, implementing the control actions, optimal operating scheme, optimal operation can be delivered. Again, uh, digital communication links are not necessary here. Here mainly the power line communication schemes are deployed. So in the decentralized approach, we'll also have to maintain the cost within certain limit. So that's why we can have the information right on that, the decentralized control action, how the decentralized control actions takes place. So next, coming to the centralized control actions. So first of all, in the centralized control actions, every source is controlled from a single location, and the communication link used is centralized. Again, the central controller aware of the entire system under operation. So here with the three areas operating under area 1, area 2, area 3. So the centralized controller is aware of all these three areas. So there's a better way we can say that the entire central controller is aware, but similarly, on the contrary, we can also will have to take this thing into consideration that and in entirety we'll have to rely on the mostly the mass communication link. Okay, so when we rely mostly on this communication architecture, so we'll have to have a reliable communication architecture or scheme, and once we have the reliable communication or architecture scheme, then we can trust them, because the issues of data uh, attacks and all these things means these things could be more and more prominent. So the reliability is mostly due to the communication links. So once these things get tampered, then the system becomes more vulnerable to some threats and all these things. But again, when the data is collected in the central controller. So once the data is collected in the central controller, that data will have to be delivered once the proper decision is made to the entire system which is downstream. Okay. So now we have the case of distributed control. Here the advantages of this is that the control action, the mostly the controlling action is distributed over the network, is distributed. Okay, so once we have the control action distributed over the network, then we can definitely say that somehow or the other, here and there, the control actions will be definitely governed by related activities which are wide open about on over the entire area and sub areas. Okay, also when we have a centralized control, then the communication failure and all these things comes into picture. But here in the distributed control, we can still maintain the other part, means we can still maintain the, means somehow if there is a failure in one communication link, but still we can maintain the information exchange from the other areas, and at least the system continuity would be maintained better than the centralized control scheme. Okay, although the communication link is much more important here itself. So control strategies, we can say the control actions or strategies distributed, and you can write it here itself, that is distributed, as well as the decision or strategies decision taken locally. Okay, so so uh, we have some of the distributed or decentralized control schemes, and here most important we have the group control schemes. Also we have the voltage leveling schemes. Also we have DC bus signal schemes, and we also have the power line signal schemes. So mostly we try to restrict our discussion in the group control activities, where we can say that when we have, let's suppose we have a group here and also another DG, they do have a, let's suppose this is the feature of one, this is the feature of DG. So we can say that with the similar change, a similar change is observed here. Here the del V, and also here in this case the del V. Both the del V would be same, but here the change which caused this del V is much different, because Q2 we can say Q1. So Q2 is much greater than Q1, but for the same control actions, both of them del V remains same. So what we can understand is that once the system behavior or centralized or group control behaviors are predominantly active, so we can, from a broader perspective, we can deliver a better system behavior, means based on this knowledge of this group control. And when we have a decentralized control facility, and we can therefore have these control actions from the central, it's not in the central facility but in the decentralized manner. And once we have the information from the decentralized manner, we can definitely give in means give our best possible information, so that the control actions can be properly taken. Okay, now there are some of the group control techniques which were discussed, like the virtual group control techniques, adaptive group control techniques, and also we can say intelligent group control techniques that last year also we discussed, and mode adaptive group control. So these are uh, a bit technical discussions on the group control or the detail of the group control. Okay, so also we have distributed control schemes, where we have the average techniques, average based techniques, digital averaging schemes. Also we have the voltage sharing schemes with pilot registration, bus registration, and also distributed cooperative control action. So these are mainly of the how this DC microgrid architecture, or in the mainly these three types of control: distributed control, centralized control, and decentralized, centralized, and distributed. Okay. So again, now comes like two major operational behaviors of the DC microgrid, that is islanded mode of operation and grid connected mode of operation. And in both of them we have uh, two basic characteristics, like here in the grid connected mode of operation, we have a substation. After the substation we have a breaker, and after that we have a bus from where the loads are distributed all throughout. And here we have the main substation, and accordingly we'll have the converter banks, because when we have a, because mostly the substation, from the substation we are having AC, but here since we are having the DC bus, so for that we need to have a converter station which converts these AC to DC. from the grid connected mode of operation. But and here we have the loads, various loads, and also we can also say that these buses also have the facilities to inject the DGs, various DGs like the solar, wind, ultra capacitor, etc. Means we have much more, but for the time being. So the advantage of grid connected mode of operation is to that when we have a share of total power that total load that needs to be shared is not possible to be delivered by this, impossible, or the total amount of load required or the demand is not matched with the total amount of DG power generation. So in those cases, we'll have to rely on the grid connected mode of operation, because otherwise we'll face blackouts and all these things. So what we try to do is that we, in those cases, and another problem is that when in the solar as well as the wind, last year also we discussed that the we have a load curve with a morning peak and an evening peak, and this cycle continues. Okay, so this one is morning peak, and this is from the Indian context itself, and the other countries will have a different loading scenario. But for Indian context, we are discussing this. So our major aim is to reduce the morning peak and improve, and also reduce the evening peak, and in the both of these cases our aim is to fill up these valleys. Okay, but the problem is that this morning peak occurs around 9 to 10 when the office during the office hours, and the solar energy which is highest, solar energy is highest during this time, and also in the evening peak the wind, this is around 5 to 6, and wind energy which starts blowing, that's in between this time. So during the peak hours we don't have the maximum output, although we are operating both of them mostly, since we are discussing both of these two type of ditches, because they are mostly predominant in the Indian context. So both of them are working in MPPT, but the problem lies is that they, when they are delivering their maximum, that is in this portion, these areas, when they are delivering maximum, there is not ample amount of load present, and when they are not up in their maximum level, load demand is maximum. So in those cases, these grid connected mode of operation do take place, and that can be uh, replaced with the advantage of the battery banks. These battery banks, they can definitely play a major role in the microgrid architecture, microgrid operation. How? So these battery banks, they have the capability of storing energy. So when we are at these when the solar energy or solar generation is at its peak, or wind energy or wind generation is at its peak, in those times we can switch on the batteries, switch on, we can store that energy, not switch on, sorry, we can store the energy, we can store the energy from this solar and wind in during this in these batteries. And when we are at the end, when we are at the what to say, when we are at the during the peak hours, means that is these point A and B. So in those cases, highlight, we are in these areas A and B. So in those cases, what we can do is that we can utilize those stored of energy in the battery to maintain a proper uh, balance, and in this way we can shift we can shift this entire operation from the grid connected to islanded mode of operation, and that too because ultimately we'll have to maintain the reliability of the power system or the power supply. Not system, we are locally concerned, discussing about the local architecture, so we can't say directly about the power system. So there are some types of islanded mode of operation, so autonomous mode of operation, multi microgrid operation. So one by one we can discuss how these operating single area, single DC microgrid operation, how multi DC microgrid operation would be advantageous, and how the various connected mode of operation like the grid connected mode of operation would be helpful in proper monitoring and in maintaining the continuity of the power supply. So in the grid connected mode of operation, the there's the connection is since in the grid connected mode, as we have discussed, that we have the supply, we have the breaker here itself, and once we have this breaker here we have the buses, the loads, all the buses present, or buses we can say nodes also. So up to the nth node we have the loads, and also some cases we can have injections, DGs. Okay, so the problem here is that here we have a bidirectional feature. Okay, not we can say the problem. We this is also we can say this is the advantage that we are getting to until and unless we have ample amount of battery energy storage systems present. We can use this grid. We will have to use this or take benefit from this grid from the grid. So grid connected mode of operation do play a major part. And bidirectional power flow. This is the bidirectional power flow that happens here. So and in the islanded mode of operation, this is the grid connected mode of operation. And we have the islanded mode of operation. So here the entire system is disconnected from the utility, and the grid has the capability to self-sustain uh, the demand. Okay, so the generation or the load power imbalance, generation and demand imbalances, which there is no imbalance, means that entire amount of generation that we have from that area will be taken care of, or the microgrid will be taken care of by the demand, will be the amount of demand we have will be taken care of by the generation. So based on these two architectures, we have types of some of the islanded mode of operation. These are mostly the broad mode of operation, and beyond this islanded mode of operation, we have single islanded mode of operation. Single islanded, and we have the multi-islanded. So here it's restricted to one microgrid. Okay, here it's mostly restricted to one microgrid, and decentralized control actions is mostly followed up. And here we have multiple microgrids: microgrid 1, microgrid 2, microgrid 3, etc. So each one of them also have the feature of communicating amongst themselves a microgrid N. communicating amongst themselves, and when we have a proper power mismatch or power imbalances, the other microgrids can also take care of the total operation, and they can be controlled in both the centralized. Means both of these control actions can be taken in the decentralized mode, and one of the microgrid don't have the capability to deliver the ample amount of energy, or the surplus amount of energy from at a point of time, the surplus amount of energy which can be taken care by the other microgrids. And if the proper there can be means in this way the reliability can be improved. Reliability improves in this type of operation. And also, like when we have multi components which are present in this entire procedure, we can at least save the control with the equipments to some extent. Okay, and stability, improvement in stability. So this is mostly followed. The market architecture is still not resolved, and mainly some global voltage regulation, some objectives that are presently being faced, that global voltage regulation, uh, power flow control, also communication based problems. So these things are also there, but still uh, each of them also the advantage of this operation is that each of them have a separate operating characteristics or operating rules and regulations, and on top of that we have a centralized feature. Means once each of them don't have the capability or to have or fails to deliver the best or optimal solution, in those cases we can definitely take care of the other other centralized controlling actions can be governed. Okay, so in the single microgrid system we can have various ones. We can have the utility grid from one side. Okay, and with the utility grid from one side we definitely need to have a grid side converter, and here we have a breaker, and after that this grid side converter converts AC to DC, because mostly the grid side is controlled by the AC power. So from the grid we are having the AC/DC power, and after that we can have loads. We can have primarily we can have a converter, DC/DC converter, and using this DC/DC converter, PV panels which can deliver the power to the grid, because PV generates in DC. So and this is DC bus. So here also we can deliver power to the grid, and there can be battery banks, as previously discussed, that nowadays these battery banks are also playing a major role to maintain or to isolate the entire grid operation, means grid connected mode of operation, and maintain the reliability of the islanded mode of operation, right? So here we have the batteries. Also we have ultra capacitors, and ultra capacitors also have generate. So mainly the advantage of utilizing this DC system or DC bus or DC microgrid is that many of these loads which are uh, governed by the which will be delivered, which will be delivered to uh, or they have the property of continuing with the DC power. So in those cases, the converter stages can be highly reduced. Here, in case of wind, the problem lies that we need two converter banks. One for, since it is generated in AC, it's DC, DC, DC. But here, since it is AC, so first the AC needs to be converted to DC, and from DC it again needs to be converted to DC converter lines, so that DC power loads, so loads can be delivered. So once this advantage, these are the boost converters. Okay, so this is single area microgrid, uh, single area microgrid. So some advantages of using this wind can be PMSG is also detailed, where the permanent magnet synchronous generators do not require any external arrangement for generating the flux, and they also uncontrolled rectifier we have to means they generate these values, means we'll have the feature of controlling. So from the DC-DC converter that is connected there in the outlet of the, or the outside part of this PMSG generator, then they also possess the capability to uh, deliver a maximum power output. So some control actions can be governed by the for these individual devices. In the loads also, their characteristics or behaviors, these loads have their individual characteristics or behaviors which are governed by their internal characteristics or impedance characteristics or resistive characteristics. Okay, here since we are mostly concerned with DC, so they are mostly governed by the internal characteristics itself. Okay, now also they are categorized into critical or non-critical loads. So demand response activities, demand response activities can be properly governed. Uh, Another thing is that the load shaving and valley filling, you can say. So load saving or peak shaving, you can say peak shaving. So after all, we are aiming to deliver a smart control and smart architecture of these modern grids, which can be in the case of microgrids, which can also be in the case of grid connected mode, means the distribution grids itself. So the major aim is that we have to have a better control feature embedded with a better communication link, and with all these things in operation, these entire smart grid control can be facilitated. Okay, also we have uh, valley filling and peak shaving, where we, as discussed previously, we try to fill this up so as to maintain a flatter voltage profile, flatter power profile. So we try to reduce this, we try to improve this. Okay, sorry, here we can say that we also try to reduce this. This is morning peak, this is evening peak. Also, we have the battery energy management systems, BEMS or BMS battery management system. We also say in some case the batteries are kept in standby mode of operation or charge discharge mode of operation. Standby or charge discharge mode of operation. Also, the charge or charge behavior or charge characteristics can be governed by the system operators, like the charge behavior is governed by the frequent switching. How the switching means, the more faster or more frequent switching actions would be taken, those would be leading to uh, charge or discharge order being impacted. Okay, so we'll have to maintain a proper discipline of how the entire things would be governed. Okay, so in the photovoltaic scheme also, there are some actions like when we have like the solar grid connected, when the grid connected mode of operations, when we are concerned about the when we are concerned about the solar power generation or wind power generation or entire grid connected mode of operation, we would say everything is connected as shown previously. In that case, the load demand load demand PL. So wind, let's say wind generation is PW, solar generation is PS, we can say battery PB. So and grid grid side generation PG. So wind, solar, and also the super capacitor PSC. Okay. So after all these things, the load minus all these things, that is PL, PW, PS, PB, PSC, that needs to be delivered by the grid side. This amount of mismatch, this amount of mismatch or surplus has to be given or delivered by the grid side. So for that case, there is voltage source converters and grid connected mode of operations, and grid side voltage source converters will have to supply the deficit amount of power, that is, which we can also write it like this way: PL minus PW plus PS plus PB plus PSC. So this much amount of power has to be delivered, power mismatch for the grid connected mode of operation. And for the islanded mode of operation, this is for the grid connected mode of operation. And for the islanded mode of operation, we will have to say that the savior here is the battery. So amount of energy that is stored in the battery PB will take care of the P load minus P wind, P solar plus P supercapacitor, because here the savior was the grid or delivered from the grid, but here we have the battery to save in contingency situation. So that's the problem, is that uh, this mismatch needs to even in islanded mode of operation. It should be assured that the PV value should be within proper range, because we will have to the SOC value, the state of charge, is generally maintained from 10 to 90%. So beyond 90% is not kept, and also less than 10 to is also not kept to maintain the proper battery life. So in these circumstances, uh, the amount of SOC in these cases in islanded mode of operation, if the SOC value comes below 10 or comes below 10, that case these cases will have to be prevented from the very beginning itself, because that would reduce the battery life. Okay, so and these cases would rise up whenever we have these two faltering. If these two means wind or solar falters at their own operating times, means solar in the morning, wind generally in the evening, although wind is all throughout the day, present all throughout the day, but generally it is considered to blow at higher rate during the evening hours. Okay, so uh, yes, so that this much amount of mode of operation should be properly taken care of, and P battery should be properly monitored, because otherwise that would reduce the overall performance of the battery. Okay, so okay, last one, this overall scheme that we have discussed, this is for the single type of operational scheme. So once we have discussed AC microgrid, and now we have discussed how the DC microgrids operate, but there are situations where both of them work in unison, and that is also known as hybrid microgrid, hybrid or AC-DC microgrid. Okay, here the control actions are much more emphasized, with proper monitoring and control actions being delivered from the uh, both AC as well as the DC part. Likewise, we have one AC bus here and one DC bus here, and accordingly, in between two buses we have interlinking converters, DC to AC and AC to DC. These are interlinking converters, and this is DC bus, this is AC bus. So we have the utility side or grid side delivering the amount of power which is required from the grid side itself, and feeding the grids from the feeding directly from the grid. Also we have the AC DGs, AC generated DGs, and also we have the DC generated DGs, storage elements, and here we can consider the same on this side also, AC gen, DC gen, and storage. So here the number of converter stages uh, impact the operational characteristics. Otherwise, the reliability of these grids are much more than the single-handed AC or DC operation. But for the AC stages, the number of converters required are much more. Okay, so and here we have the AC load, and here we have the DC load. Directly we can feed on. If we can need to feed AC load here this side, then before that we need to place one converter bank. So here we have the DC. So when we are generating in AC, so we'll have to AC to DC converter needs to be placed. Since here it is in DC, So directly we can feed by DC-DC uh, converter loop, and here we can have bidirectional. Similarly, here also we can do bidirectional, but here we need to have three stages from the AC to DC to AC. Okay, and here it is directly DC generating DC to AC. Here it's bidirectional. For DC AC loads, this is DC, so we'll have to convert them to DC to AC. And again, for the AC load, it's working fine, but for DC loads, again we need to convert them AC to DC to loads, means DC loads. So the main advantage of both AC/DC hybrid coupled microgrid is that whenever we have a mismatch, this is the grid is connected from the in the AC side, and when we have a sudden mismatches between the both the AC and in any of these areas, in the DC side grid or the AC side grid, in those cases we can directly deliver the power from the AC side to the DC side using the help of these interlinking converters. Okay, and these hybrid architectures control strategies that we need to uh, take up is that these they have the power management schemes we as we follow. So the active and reactive power that we have or that we generate or we take directly from the grid, they both of them need to be properly monitored first. Okay, and accordingly these voltages and frequencies has to be maintained within their proper limit at the same point of time. So overall efficiency, we can say overall improvement in efficiency, improvement, improved efficiency, but we can say challenges is that both the PF and QV side, conventional in the autonomous mode of operation that we had is PF operational and QV operational schemes that gets affected to a greater extent by the group control strategies, and also the power management schemes that we have in this architecture in these architectures, that the power management schemes should be uh, properly handled by the AC and DC group control features, and a proper emphasis needs to be given directly or indirectly to the active or reactive part. Means there will have to be a trade-off between the reactive power sharing and the voltage regulation schemes. So here also the connect operating modes that can be seen here is the both the grid connected or islanded mode of operation So in the grid connected mode of operation, we have dispatched mode of operation and we have the undispatched mode of operation. And in the dispatched mode of operation, the the microgrid mainly behaves as a controllable source. Okay, and in the undispatched mode of operation, the or in the grid connected undispatched mode of operation, we can say power is fed to the grid and the DGs works in MPPT. Okay, and the means mostly they can be controlled in this Smooth power output, no oscillations. Oscillations would be smoothened out, and all these things. Undispatched mode of operation. And in the standalone or islanded mode of operation, there are interlinking converters which do play a major role in ILCs, interlinking converters. So from switching actions between these control actions between these mode of operations can also be taken place switching actions between these grid connected and these islanded. So these two sides will have to be taken care of. Alongside to it, we can also have the concept of in the standalone section or the islanded mode of operation, we have the passive synchronization as well as the active synchronization. And in the passive synchronization or active synchronization, both of them with the microgrid voltage in the passive. Let's discuss the passive first. The microgrid voltage will have to be uh, synchronized with the main grid side voltage, and the two grids would be connected. Okay, first, and after that, the standalone to grid means this is from the standalone to grid connected mode of operation when the connection is being done. Standalone to grid connected, these control action means when this transition is taking place, one is passive synchronization and another is active synchronization. In the passive, this voltage and grid side voltage will be checked, and both of them will have to have the same phase angle. Okay, but in the active mode of operation, active synchronization, one or two DGs initiate the synchronization process, and the subsequent DGs try to follow them up. Okay, and every DG has to be synchronized. DG synchronization must. Okay, the some there is a stage wise means the first group of synchronization strategy is mainly due to the microgrids with some of the DGs working alongside to it, and further some DGs when some of the DGs have already been connected or already been synchronized, then further subsequent microgrids will be connected with the at the point of zero crossing. Okay, so hybrid microgrid schemes, there are future objectives or aspects that can be fulfilled with the aim is to uh, maintain the power management schemes. Also, there's an aim is to maintain the transient power characteristics, transient power management. Also, we have the maintain the economic aspects. Also, we need to take care of the quality of power and communication side improvement. So these are the future objectives that needs to be encountered as a part of hybrid AC/DC microgrid need side. So and also the parallel ILC operation, that is interlinked converter operation. So that is the overall significance of how the things to operate, and so this is the overall idea of how microgrid systems operate AC/DC, AC/DC, both AC/DC as well as the DC, etc. So overall, that's the architecture we need to follow up. So accordingly, that's the overall overview of this week's discussion. So we'll discuss some questions, and once if the time permits, we can discuss more of them. But for the time being, uh, we can discuss some of the questions. Okay, let me. So I think questions are visible, so you can participate in the question discussion. So there's a on the front slide the date is not changed. It is written mistakenly. So I'll change the date and upload this thing. So okay, the first question. So some questions are there. We can discuss them in the AC microgrid. The global control. Excuse me. AC microgrid. The global control. We have to emphasis on the term global. This is all references from AC microgrid. You can write in the chat box also, or you can open up with the discussion by switching on the mic. The AC microgrid, the global control receives power references from distribution substation, distribution protection system, distribution management system, all of the above. So this answer will be distribution management system. Okay. Okay. So back to this question. So in order to improve power sharing in group control, what kind of component is connected between the power converters and the AC bus in virtual impedance based control? So virtual impedance based control. So here are some key points. So improve power sharing in group control. So we have to improve the power sharing in group control. Type of component connected between power converters. Which component needs to be connected? Which component needs to be connected between the power converters and the AC bus in a virtual impedance based control method? The component is connected between the virtual connected between the AC bus and the power converters. Which electrical component? I am also saying that which electrical component. So here we have inductor. Inductor is connected. Okay. Now the conventional group control in a DC microgrid. Conventional group control in a DC microgrid reduces the reference DC bus voltages, which leads to increase in output current, decrease in output current, increase in power output, all of the above. The conventional group control of a DC microgrid reduces the reference bus voltage, lead to a increase in output current. Okay. The conventional group in a DC microgrid reduces the reference DC bus voltage, leads to increase in output current, decrease in output current, increase in power output, all of the above. Am I audible? Right? So our aim is to in the group control method, mostly our aim is to deliver the imbalance. Okay, and to minimize the imbalance caused between the generation and as demand. So that's our aim. With this aim, so we'll have to increase the output current whenever this reference DC bus voltage with the reducing DC bus voltage. The interlinking converter in hybrid AC/DC microgrid ILC ILCs. The interlinking converter in this hybrid AC/DC microgrid during grid connected mode operates in DC bus voltage regulation mode, AC bus voltage regulation mode, power dispatch mode, none of this. Grid connected mode of operation. So we'll have to emphasize on these terms. Grid connected mode, hybrid AC/DC microgrid, interlinking converter. How the interlinking converters operate, in which mode of operation they operates. Grid connected mode of operation, hybrid AC/DC microgrids, interlinking converters, how do they? So here it will be DC bus voltage regulation. Now coming to global hierarchical control is a centralized control, decentralized control, distributed control, either of centralized or decentralized. So global hierarchical control. This is centralized control. The ultra capacitor, which is connected to a DC microgrid along with the battery, is a dash device. High power density, low energy density, low power density, high energy density, high power density, high energy density, high power density. As a last two, this is last two options are same. So discard this one. High power density, low energy density, low power density, high energy density, high power density, and high energy density. Which of these characteristics are when battery along with ultra capacitor? What is battery? Just a reverse of that. Battery is low power, high energy, and it is connected with the ultra capacitor to mitigate, or to say, we can say that, to maintain the behavior of the entire system. So here we can say that the ultra capacitor is a high power density, low energy density. So when both of them are connected, the entire operation becomes much more reliable. Okay. Next, poor voltage regulation in droop control DC microgrids is due to large droop quantities, small droop quantities, dissimilar power capacities, none of the above. Poor voltage regulation. So what will be the answer? Large droop quantities, right? Now coming to the entity, which of the following entity is responsible to maintain the DC bus voltage in grid connected DC microgrid? Which of the following entity is responsible to maintain the DC bus voltage in grid connected DC microgrid? Voltage source converter interfacing DC bus to utility, battery connected to DC bus, PV connected to DC bus, both PV and battery connected to DC bus. So it will be voltage source converter interface DC bus to utility. The battery connected to a DC microgrid is a dash device. The battery connected to a DC microgrid is a dash device. Low energy and high power density, low energy and low power density, high energy, high power density, high energy, low power density. Now it's about the battery. Lastly, it was about the ultra capacitor. Ultra capacitor was high power, low energy density. And about the battery, it's so it will be high energy, low power. Now, in the hybrid energy storage system, which of the following devices help to compensate for high frequency switching transients? Battery, supercapacitor, superconducting magnetic energy storage, SMES, or capacitor? Hybrid energy storage system. So here it is supercapacitor. With the DC microgrids operating with adaptive resistive droop control fails to ensure proportional power sharing among sources, mitigate circulating currents, maintain SOC balancing among energy storage systems, all of the above. DC microgrids operating with adaptive resistive droop control. Adaptive resistive droop control maintain SOC balancing among energy storage systems. Okay, that's now an islanded hybrid AC/DC microgrid has excess renewable energy and fully charged energy storage systems feeding uncontrollable loads, both in AC and DC buses. The possible solution to maintain system stability is load shedding, operating renewables in power dispatch mode, charging energy storage systems, none of the above. Operating renewables in power dispatch mode. Which of the following statement is true in grid connected operation of AC microgrid? Grid connected operation, AC microgrid. Battery charging, PV at MPPT, diesel generator regulating the voltage and frequency. Battery charging, PV at off MPPT, AC microgrid and grid connected mode of operation. We need to keep these two things in mind. Diesel generator regulating at voltage and frequency, battery charging, PV at MPPT, diesel generator turned off. Battery discharging, PV at off MPPT, diesel generator regulating the voltage and frequency. So it will be battery charging, PV at MPPT, diesel generator turned off. Okay. So grid connected mode of operation. You need to keep these things in mind. So overall, these things are. This is the overall summary of this week's lecture and of the week's lecture contents given by the professors and some questions that we have discussed. So if you have any doubts, you can ask. Otherwise, we'll conclude the session and end for today. And next Saturday, we'll meet with the next week's content. Overall content. So if you don't have any queries, then we can meet them in the next two. Okay, thank you for joining.